Okay, so on Friday we ended with surface tension. I was talking about how water is kind of sticky. What types of bonds hold water molecules to other water molecules? It's an intermolecular force, but which one specifically? Hydrogen bonds, and they're very strong. It takes a lot of force to actually break them. So water, like you may have never described it, heard it described before, but it is sticky. And the water bonds to other water molecules because of the positive poles and the negative poles. And you got insects like this water strider, they're able to push down on the water and not break the surface. Normally, if we were in a regular science room, I would show you in a demonstration where if I had a cup of water and I filled it up, you would actually see the water level rise above the top lip of the cup without spilling over, because with the forces of gravity and water and surface tension, the water is able to stick together and actually not overflow. Obviously, it will overflow because gravity will really overwhelm it. But if you go home and you try that, you fill up a cup of water, you can actually get it to rise above the lip of the cup because the forces of gravity and surface tension are keeping all that water sticking together. The water is very high surface tension. Surface tension plays a role in removal of dirt from skin. If I had a bunch of dirt underneath Kendall's desk, I say, Kendall, here's paper towel. She has a dry paper towel. She tries to scoop it up. It's not going to come up as easy. But then she goes and gets a little damp, and she's pressing down on the dirt. It comes right up because water is sticky. It has an adhesive and cohesive property. It will stick to other polar surfaces. If you got dirt like all on your body, you got a dry paper towel, it's not going to come off as quickly as if the paper towel was wet, because the wet paper towel is covered in water. Water is polar, and so it's able to grab onto all other polar surfaces. That's called adhesion. So I have a few images here I want you guys to see just to demonstrate the surface tension of water. On the left, you can see an Olympic swimmer. Look at the water has not broken on their body. It's all still together, intact. Here's a jaguar coming out of the water. The water is not broken, or broken surface, or the animal has not broken the surface of the water. And you have a spider rolling up a bead of water. Those are all not photoshopped. I can think of another one. Let me show you. Pull up here. Oh no, actually I have it on my computer. Right there. That shark has not broken the surface of water yet. Now, obviously, everything in nature has its limits, and if that shark swims up with enough force, it is going to break the surface tension and come smashing out and eat whatever it's going after. But that's all just known as surface tension, where the water is strong enough to stick together, especially due to the influence of gravity. All right, now the differences between adhesion and cohesion. Cohesion is water sticking to water. Adhesion is water sticking to other polar surfaces. So if you have dirt on the floor or dirt on your hands and you use water to get it off, that is adhesion. But when water sticks to water, like in a puddle or in a stream coming out of a faucet or a hose, that is cohesion. All right, so cohesion, think of like a coworker or a co-author. You're both authors, you're working together. Cohesion, you're two water molecules working together. Adhesion are going to be water and then just another polar surface. It could be a leaf, it could be your arm, it could be the floor, anything like that. All right, capillary action. This is how we're actually able to have blood flow up despite gravity. This is how in a plant, xylem is able to bring it's able to bring water up from the roots to the leaves. It's known as capillary action. Water is drawn into narrow tubes in spaces, and water is drawn to these tubes in these spaces, which means these tubes in these spaces must be polar. If I give you a piece of printer paper to mop up a spill, it will not clean up the spill as well as a paper towel, because the paper towel is engineered to have little pores all over, which, for lack of a better word, sucks up the water. Printer paper doesn't have that. And so that demonstrates capillary action. There's little pores that are able to draw the water up. Printer paper or notebook paper doesn't have such things. It's also how we're able to circulate blood throughout our body. Our body is mostly made out of blood. Or excuse me, our blood is mostly made out of water. It's also how plants are able to get water from roots in the ground up to the trees and the leaves. They're able to defy gravity because they're, again, lack of a better word, they're being sucked up. That's the capillary action. Those surfaces, the xylem, your blood vessels, they're polar, so they're able to attract water to go up. Paper towels must be polar too. That's how they're able to draw in that water. And now we get to solids. Is there movement of particles, atoms and molecules and compounds within a solid? Are they moving?
Yes.
Yes. Are they moving a lot? No. At what temperature will they not move at all? Zero kinetic energy.
Absolute zero.
What is absolute zero?
0 Kelvin.
0 Kelvin. Good. So there is movement in solids. There's not a lot of it. Well, the kinetic molecular theory applies to gases. It applies to liquids. It doesn't apply as much to a solid because solids really don't move that much. But here's my question I'd like to ask you now. How come right now this classroom is currently at 73.1 degrees Fahrenheit? Why is this podium solid, this water liquid, and this carbon dioxide a gas, all at the same time? Arshan?
They all have different melting points, boiling points.
Everything on this earth and everything in this universe has a different temperature in which it can make a solid, a liquid, or a gas. Everything is different. In hospitals, doctors use liquid nitrogen to preserve things like egg cells or organs. If my sister had in vitro fertilization, her and her husband were having a hard time getting pregnant, and so what they did is they took his sperm, they took her eggs, and a doctor literally put them together in a laboratory, and then put them in a little petri dish, and a few days later there were embryos growing. An embryo is just a little cell ball. And they told my sister and her husband, okay, we have 7 embryos. How many do you want implanted into your uterus? And this was about 12 years ago. So with that technology at the time, the doctors would say, if I implant 3, odds are you'll get 2. You could get 3. Don't kill me if you get 3, but the odds are you'll get 2. If I implant 2, you'll likely get 1. You could get 2, but the odds are 1. What do you want to do? So they implanted 3 into her uterus, and true enough, one of them died, the other 2 survived, and they had 2 daughters. Well, what I'm getting at is, let's say that, so my sister and her husband, they had 7 embryos. What do you want to do? If we implanted 3, what do you want to do with the other 4? And people do this. I know another couple that did this. They'll say, put them on ice. And what they do is they use liquid nitrogen. Now, right now, in our atmosphere, it's warm enough where nitrogen is a gas. You have to get nitrogen really, really, really cold to get it to be liquid. So cold, it's like, I think it's probably more than negative. It's between, I would say, somewhere around negative 200 degrees Celsius. It's really cold. And they preserve these things. So let's say 5 years later, my sister and her husband go, you know what, we'd like another child. Let's get one of those 4 embryos that you put on ice. And so the doctors will go to the liquid nitrogen tank. They'll withdraw those 4 embryos that are still alive. And I don't know what process they use to thaw them out, but they'll take one and they'll put it into her uterus. I'd surprised that they They had 5 embryos. They implanted 1 in her uterus. 9 months later, little boy. She wanted to have another pregnancy. Okay, let's take one of those ones that we froze, put it in her uterus. Another little boy. All right, let's put 2. She wanted 2. Put 2 in there, got twins. And so people do this with organs. They do this with tissues and cells. But the point I'm making, you guys, is what Arshan said. Everything has different temperatures. Water freezes. Let me ask you this: at what temperature does water vapor become liquid water? 100 degrees Celsius. And you might be thinking, well, I thought that's when water turned into a gas. You're right. But the door swings both ways. You guys just walked into that door, there's an entrance. You walk the other way, it's an exit. So let me ask you this. Let's say right here, I'm liquid. This line is 100 degrees Celsius. I'm liquid. What am I now? Gas. Now let's flip it. What am I now? What am I now? So it goes both ways. You have to expand your mind a little bit to think like that. Water will turn into a liquid from a gas at 100 degrees Celsius. For nitrogen, it's like negative 200 degrees Celsius. I'm not entirely sure about that, but it's pretty cold. So everything on Earth and everything in the universe has different freezing points, different melting points, different condensation points, and different boiling points. Everything is different. And it's all about the forces, the bondings that are within those substances. When it comes to a solid, the forces that are present within a solid are stronger than any other state of matter. Obviously stronger than a liquid, and you should know that there are no attractive forces within a gas. So it's kind of a trick question when I ask you what has a stronger bond, a solid or a gas? Well, there are no bonds in gases, so definitely solid. Yeah.
Like wood melt.
Wood, well, it depends on what it's made of. It's mostly made out of carbon, and carbon is combustible. So you have to keep in mind that things are combustible. Particles in a solid are in motion. They're just not moving a whole lot. It's like having really tight handcuffs. If I put one of you in handcuffs, you might be able to do this. Wiggle your wrist. You can still move, but you can't move a whole lot. If I had looser, less restrictive handcuffs, you can do this. This is like a liquid. And if you're a gas, you have no handcuffs. You're free to just move your arms wherever you want. Remember that the stronger the bonds, the less the kinetic energy. Kinetic energy is all about movement. Last week, Derek slapped his hands together and run them really fast. That gets heat. The hotter things get, the faster things move. In your car, you have a heat gauge. The faster your car moves, the hotter your car gets. A car that's going 50 miles an hour is going to be hotter than a car going 20. There's also more order in solids. It's more organized. Let me ask you all this. What state of matter is glass? What does glass come from? How do you get sand to become glass? Okay, what is the definition of melting? From what state to what state? Solid to liquid. You have sand, you melt it. And this happens in the desert all the time. Lightning strikes the desert, you got a little area of glass. You melt it, and then it cools. Now you have something entirely different. Doesn't crystallize. Well, I know why you would think that. Those are called amorphous solids, solids without form. We'll get to those. Just to get you thinking a little bit. All right, let's talk about density of solids. Water is weird. In my biology class, AP Bio, the first thing I go over with my students on day 1 of the school year is the chemistry of water, because it's the stuff of life. But it's weird. You all hopefully know that during the medieval ages, blacksmiths would melt iron. They would have a furnace, and they would have iron, and they would melt it. And then they would pour the liquid iron into a mold, and the mold would cool. And then they would take their hammer and pound while it's soft and it's still kind of liquidy a little bit. It's like a really soft solid. They would pound it with their hammer, pound it with their hammer, pound it with their hammer to get it into like the shape of a sword. And then they would immediately dunk it in water to cool it to permanently freeze it in that state. So you get this nice, perfect, awesome sword. Well, imagine this. You have a sword made of iron, and then you have a pool of melted liquid iron. Would you expect that sword to sink or float? In other words, I'm asking you, would you expect the solid, the sword, to sink in the liquid iron or to float in the liquid iron? Sink. In 99 times out of 100, the solid form of anything is going to sink in the liquid form of anything. What the heck is going on with water? Solid particles generally are more dense. They're more tightly packed together. And that means that they have a lot of mass over volume. You know, like I like to joke that bulldogs, you know, English bulldogs with the big smashed in faces, they're not that big, but they're incredibly dense dogs. You ever picked up a bulldog? They're like a bowling ball. They're small, but they're heavy. That means it's very dense. It does not take up as much space, but it has a lot of mass to it. If you go to the gym, my nieces, I was just talking about them, they're probably around 60 pounds right now. They're not that big. If I was to pick one of them up, it's going to feel not that much. But what if you go to the gym and you pick up a 60-pound dumbbell? It just feels heavier. But my niece, a little 11-year-old, is the same weight as this 60-pound dumbbell, but there's a different density. My niece has 60 pounds distributed across her whole body. This 60-pound weight has 60 pounds all centrally located in that one little hand weight. And so that means that the weight is more dense. It has a lot of mass, but in a little bit of volume. Volume is space occupied. So that means all the particles are really smashed in together as much as you can get. That is generally what you see in solids. The particles are very much close together. Like here's a gas, here's a liquid, here's a solid. Very close together. Water is different than this. Water violates the rule. So what I'm telling you is the rule is solids are very close together. They're particles, they're atoms. Water's weird. Water floats in its solid state when you place it into its liquid state. What does water do when you freeze it? It expands. That means that it is less dense than its liquid form. Science 101, guys. Something that is less dense than an object you place it in will float. Those big giant cruise liners that come to Tampa all the time, they are less dense than the water underneath them. They might be made of these huge vehicles of iron and steel, but they have a lot of cavities in them, a lot of air pockets, a lot of rooms, a lot of open spaces. And so that means that they're not as densely packed as you might think, and they actually float. That means the ships, Titanic even, were less dense than the water underneath them. If something is more dense, it will sink. If something is less dense than the water, it will float. So basically, all things being equal, let's say water is rated at a 1. If something is less than 1, it'll float. If something is more than 1, it will sink. If I give you a spoon and your spoon sank, it is more dense than water. If I gave you a leaf and the leaf floated, the leaf is less dense than water. Ice is weird. It is floating in its liquid state because it is less dense. That's the violator of the rule. That's the exception to the rule. This is why in Texas there were burst pipes everywhere. People didn't have water because Texas is in the south. They're not used to things being that cold. Same thing down here in Florida. Whenever we have a water main break because it got into freezing temperatures, the water in the pipes expanded because it became ice, and it didn't have anywhere to go except break the pipe. If you filled up a glass bottle with water and you placed it in your freezer, you'll have shattered glass everywhere in your freezer when the morning comes because that water expanded. All right, let's get to solids. Crystalline solids. I said that they're more organized. A lot of solids form a geometric pattern. Emma, the doodler. A geometric pattern is an alternating sequence of the different elements. Like in a cube of salt, you have alternating chloride ions and sodium ions at a 1-to-1 ratio. It just depends what the ratios are. This is called a crystal lattice or a crystalline solid. They're arranged in a very organized, very sequential geometric pattern. And it's all based on the ratio of the atoms or ions that are present. So, like if you have a sugar cube, like glucose, it's C11H22O11. So for every 11 carbons, you're going to have 22 hydrogens and 11 oxygens. So it's going to be basically a 1-to-2-to-1 ratio. For every 1 carbon, you're going to have 2 hydrogens, you're going to have 1 oxygen. This could be salt. Let's say the greens are chlorine, the yellows are sodium. So it's a 1-to-1 ratio. Sodium chloride, NaCl. So you got chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium. In that ratio, 1-to-1. So a unit cell is the smallest representation of the entire crystal lattice that still represents that same ratio. So if this were sodium chloride and it's a 1-to-1 ratio, if you guys look down here in the image, I think I found a pretty good one for you. This entire structure here is a crystal lattice, but one little component of it, one little ape, is going to be a unit cell. That unit cell is indicative of the entire structure. So let's say that Plain High School had a ratio of 4-to-6. For every 4 boys, there are 6 girls in the whole school. Let's say this classroom had that same ratio. For every 4 boys, there are 6 girls. This room would be considered a unit cell of the entire school. You are a smaller segment, but you are still representative of the larger whole. So if this is a 1-to-1 ratio of, let's say that's sodium and that's chlorine, so that's 1-to-1 ratio, and the whole solid is a 1-to-1 ratio, then this is indicative of that. All right. And this gets me to the glass. I'm going to show you guys a video here of how they make glass. Let's see what time. Let me get out, 10:45. Okay. A glass, anything. A glass bowl, a drinking glass, a plate, whatever, is called an amorphous solid. If you put the letter A in front of a word, it means the opposite. Morph means shape. Amorph means without shape. These are solids that do not have an actual structure. Amorphous means without shape. It is a solid. But unlike traditional solids, there is no pattern of like organized geometric crystalline pattern that keeps them in place, which is why if I drop this marker, it didn't shatter because it actually does have an organized structure to it. And that organized structure helps make it pretty durable. But when you drop glass, it shatters everywhere because there's really no structure there holding it together. Typically, when you have things like glass, they were super cooled too fast for a structure to actually form. And so they're very fragile. When I say it does not contain crystals, what I mean by that is it does not contain an organized geometric pattern, which is why they shatter so easily when you drop them. The way that glass is made is you typically have the ingredients for glass, which is generally sand and derivatives of sand, and you superheat it, and then you sculpt it into whatever shape you want it, and then you cool it off. And it cools so fast, it can't form a proper geometric structure. And so it's not really holding on to, it's not holding together as well as traditional solids would. So things like rubber, glass, and some plastics, those are called amorphous solids. They don't hold together as well as your traditional solids would. Yeah.
If it like slowly cold glass, could it get one?
It would likely have a more defined structure than rapidly cooled glass. Yeah. But time is money, and people always buy glass. They don't do it for science experiments. All right, so I want to stop here. Let me turn off the recording.